Now, the most awaited things to watch, Spark, which predominantly concentrated in our interviews. During the interview time, they may ask you some scenario-based questions as well. That scenario would differ to a company, person to person. However, it's better to have some good knowledge on hands-on, like data frame operations or SQL operations, in which we'll be seeing in our some of the scenarios in our SQL section also. But however, Spark is very crucial. 70% of the interview weightage would be going to Spark. So we have hardly 40 to 50 questions predominantly asked in Spark. So let's get started. The first thing, what is Apache Spark? Apache Spark is an open source distributed processing system for big data workloads. It utilizes in-memory caching and optimized query execution for fast analytics query against data of any size. So first of all, Spark is an open source in-memory computation framework, which would help you to process very faster without hitting the hard disk. That you can say. Let's go next. How is Spark different from MapReduce? Spark does process in memory without hitting the hard disk. However, MapReduce hit the hard disk for every action of MapReduce job till the completion. So, as I was explaining in the Spark and MapReduce jobs, I should have explained for every transformation of MapReduce, it keeps hitting the hard disk. Like if I'm performing any transformations, like if I have this as a hard disk, if I have this data here, if I have the raw data here, after if I trigger some transformation or filter at anything, this data comes back, gets filtered, and hit the hard disk. It'll hit the hard disk. Then again, some other transformation will work. Then again, this keeps hitting the hard disk. So this is what the MapReduce job is. So since Spark is lazy as well as in-memory computation, when the data gets loaded, it will just create the plan. When to apply the filter, it just creates the plan. When to do another transformation, it create the plan. By the time I give some actions like write or save or print, then the data comes in. Then the lazy evolution starts. Data gets replied here, data gets processed here. As usual, it will go like that. So it will not hit the hard disk. So Spark is far different than MapReduce when it will not hit the hard disk. Very important question. Let's go next. What is lazy evolution? Till the action is triggered, none of the transformation takes place. So Spark lazy in nature, as I just explained in the previous question. What are libraries of Spark? RDDs, data frames, MLlib, streaming, structured streaming, and graphics. Ways to process data in Spark. That could be RDDs as well as data frames, or also we have data sets. Data set is just a subset of data frames, not as good as data frames in performance. So predominantly in real time, we go with data frames. Schema RDD in Spark. If any of the schema is imposed on Spark RDD using case class in Scala or named tuple in Python, we call it as a schema RDD. What are the save modes in Spark? When I write the data, we have to, using a data frame, we have modes. Error is a default mode. If the directory already exists, it would error out. If a directory already exists, it will append to the it will append the file to the same directory. If it overwrites, it will overwrite the whole directory. Ignore. If the directory already exists, it will simply ignore the write. Folks, the significance of save modes you will see predominantly if the directory already exists. If the directory does not exist, save modes will not have an impact. It will create a directory and write the data. Save modes will come into picture only if the target directory exists. Next, default file format in Spark. Spark is the default file format. Spark also supports JSON, CSV, ORC for other file formats. For other file formats, we need extra dependency like Avro or XML. We need extra dependency. And we have that formula, Spark read format options load. Next, very important question. Explain how Spark runs applications with the help of its architecture. When Spark submit is done, Spark context gets created in which it runs a driver program, which submits a job to the cluster manager, which in turn communicates with each worker nodes where the executors are created to run the task and caching the data. Imagine once you do a Spark submit, the Spark driver program gets created in the edge node first. It's a kind of a client. So this driver program will communicate with the cluster manager. Cluster manager can be Yarn or any other, right? Resource manager in case of Yarn. It gets communicated to the cluster manager. This cluster manager will communicate with the worker nodes or else data nodes in other words. Then it creates an executor. Executor is a kind of a space memory where the task gets created, individual tasks. So caching is another area. If you want to cache the data, the cache will be performed. So on whole, it'll first when you do a Spark submit or when you open a Spark shell, driver program gets created. Then from the driver program, it submits a job to the cluster manager. Cluster manager will communicate with the worker nodes to run the MapReduce jobs in memory in Spark. Then executors gets launched inside it, which the task gets created. If required caching, the caching would happen. So this is the Spark architecture. Very common question in interview time. Next question. What are the different cluster managers available in Spark? Standalone cluster, if we don't install Hadoop or any other thing, it runs on standalone. Distributed environment. If we have Hadoop environment, we can run it on Yarn. Without any such situations, we can go with Apache Mesos also. What is RDD in Spark? RDD are main logical data sets in Spark. They are the distributed collection of objects which are stored in memory or a disk of different missions of a cluster. A single RDD can be divided into multiple logical partitions so that these partitions can be stored and processed on different missions of a cluster. What does that mean? Imagine when I deal with a distributed environment, I have different nodes and it's different in memory. Imagine this is RAM. I may have the data sitting in our two different nodes like this. Imagine this way. When I try to read the data, according to you, it's a single file. But when you read the data, where data is equal to sc.text file and give the path of the HDFS path, maybe it's just a single path for you, but the data should have been distributed at the backend. This data that comes to RAM, this data also comes to RAM to get processed because I am reading this data and giving this path, and this becomes my RDD, which is nothing but data in this case. Data is an RDD here. My data variable is an RDD. This becomes RDD, right? So when I read the data, when I give the path, maybe that path data might have multiple blocks. I'm assigning an RDD to process it. So that's what RDD, resilient distributed data sets. Let's go next. Shuffling in Spark, very common question. What is shuffling in Spark? When does that occur? The Spark SQL shuffle is a mechanism for redistributing or repartitioning a data so that data is grouped differently across partitions. Based on your data size, you may need to reduce or increase the number of partitions of data frame using Spark. What is actually shuffling mean? Imagine I have a cluster. Imagine I have a cluster. If I have data set sitting in this cluster, if this is one of the data sets, this is another data set sitting in a clusters. Now what happens? Shuffling is nothing but data shuffling between the nodes. Simple words, right? If I'm performing any resizing the partitions, resizing partitions you'll get to know in the upcoming questions. When I perform resizing the partitions, it will ensure this data gets shuffled to the next data set. To equalize the partition size, you'll get a clear understanding with coalesce and repartition topic in Spark, which is going to come. But what is shuffling? Simply a data shuffling. To equalize the partition size during the increase and decrease mechanism of partition size, data shuffling would happen to maintain the equal partition size, which will be known as shuffling operation. In simple words, shuffling is a mechanism helps to equalize the partition size during repartitioning. What is repartitioning? We have a separate topic coming down. You can say this as a definition. Let's go next. What is Spark session versus SQL context? Spark session is SQL object to perform SQL or data frame operation. Spark context is RDD object to perform RDD operation. Let's go next. Another important question, narrow and wide transformations in Spark. Narrow transformation, transform data without any shuffle involved. Wider transformations, the results like group by and reduced by key functions that compute live on many partitions, meaning data movement between partitions. In very simple sentence, what is wide transformation? Transform data with shuffles. What is an example? I'll tell you. Best example is filter, flat map. All these are narrow transformations. Group by key, reduce by key comes under wide transformations. I'll tell you what is it. What is narrow transformation? Imagine you have two data sets in a node. And I read this data using val data is equal to sc.text file. Imagine this way. If I read this data, val sc.text file. Now what it will do, when I perform an action, obviously this data will come out to the RAM to get processed. Imagine the action is triggered because it's lazy, right? So it will read. Next, what am I doing? I'm performing a filter. Val fill gym is equal to data.filter. Imagine I'm applying a filter. It's a narrow transformation. Shuffling is not required. This is a data, right? When I perform filter, it can individually do the filter. There is no dependency between one node to the other node. It will give some result. This will give some result. This is narrow this is narrow transformation. Shuffling is not required. When I performed a group by, fill gym.group by, yes, we have a dependency. Group by key. Imagine there's something as group by key. That performs wider transformation because when I perform a group by, that group by need the full data set. The shuffling will happen and that gets performed. Group by key. This is a wide transformation. In simple words, if I have the shuffles, it would, for any of the transformation, data shuffling between the nodes, that is wider transformation. The shuffling is not happening. That is a narrow transformation. That's what I have put here. Best example is filter and flat map. In this case, group by key or reduce by key. Cache and persist. Extremely important topic. Right? There is no interview maximum without this question. Caching or persisting mean caching the intermediate process data to reduce the redundancy of same execution. Cache and persist do the same, but cached data cannot be uncached. Persistent data can be unpersisted, and it has a different storage levels as well. But what is caching? Imagine I have a code. Val data is equal to sc.text file. I read the data. Val fill gym is equal to data.filter. Imagine contains gymnastics. Val male data. Imagine male data. Fill gym.filter contains male. And imagine male data dot for each printer. And I put another transformation. Imagine I put another transform. Val female data is equal to fill gym dot filter contains female. Female data dot for each printer. In this case, have a look. First, how the program gets executed. First, transformation gets started. It will load the data. It will filter the data. It will filter some more filter on fill gym. And on top of it, the print would happen. Right? And once this print gets done, immediately this data gets removed from the RAM. This data gets removed from the RAM. This data also gets removed from the RAM because that's a lazy evolution. It goes in reverse. Then again I filter, hey, fill female data, fill gym, filter contains female. Again, it will go back to the fill gym. Again, it will load the data. So 2 times I'm loading the data. 2 times I'm performing the contains gymnastics filter. Because once the action is triggered, unnecessarily I'm performing the same transformations again. What if imagine if I make fill gym dot persist, what will happen? Data gets loaded. Once I print data gets loaded, filter would happen. Persist means I created one line here. Then mail data, and once a print is done, it has to remove everything from the RAM because the action is completed. But it'll remove everything. Fill gym stays back because I performed the persist. That time when I perform fill gym, it will not load the data again. It will not filter the data again because we have fill gym ready here. So it will directly perform the contains. Let's show it as an example. Imagine this is my Spark shell. Yeah, imagine I have a Spark shell open. I open Spark shell. Now let's read data. For example, val data is equal to sc.text file. Imagine I read txms file, just a normal file read. Then val gym data is equal to data.filter, right? X lambda x dot contains gymnastics, right? I perform this. Gym data dot persist or cache. Both would do the same, okay? But you can give gym data dot persist. I persisted it. Val cache data. I'm still performing another filter on top of gym data. Val cache data is equal to gym data dot filter x lambda x dot contains cache. Val credit data is equals to gym data dot filter x lambda x dot contains credit. Now have a look. Analyze the code. First I read the data. Next I filter the data. And I'm persisting gym data. The reason, I have worked with gym data twice to filter the cache data, to filter the credit data. So that's the reason I persist here. Now what I do, have a check. I just opened a Spark UI also to show you this. How to open a Spark UI. There is a link. When you open the Spark shell, it will provide you. Let's open this link. You will see Spark UI coming up. This is Spark1. Alright. So in this Spark1, you can see the running jobs, stages and everything. So concentrate here. If I have the Spark UI, right? Check here. I do not have any actions performed here. But no storage also. Storage is also very important section. No storage, no jobs, nothing triggered because none of the actions has been triggered. No storage panel also. Now what I do, I'm going to trigger cache data dot take. I'm going to take only 5 lines for each println. Now I'm going to print an action, which is nothing but an action. I'm going to print the cache data. Once you trigger that, now it will go back, lazy evolution, it would print. If you see the status in Spark UI, you refresh this, you will see a take command, take of println command has been triggered. But my gut feel is gym data is set in the memory. If you want to check whether it got persisted, go to storage. You will see it got selected. See, map partitions RTD. This got cached. Right now, gym data is sitting in the cache right now. All right, in the persistence. Now I perform another action. Create data dot for each println. I'm performing it. Shoot. Now immediately it prints because gym data is already sitting because cache created as has a dependency of gym data. Now gym data is already sitting in the RAM because the previous action itself it got persisted. So it will be very faster. It will not load it again. It will not do the filter again. It will be done. Once my work is completed, see 2 actions you will see in jobs. One take some time ago and recent take has come up. Now still the data is sitting in RAM. Gym data is still sitting in cache in RAM. Right? Now, I'll remove that. Gym data dot unpersist. Triggering it will go out of the RAM. Now check. It will go. This is what? Cache and persist. The major cache and persist will do the same, but once you cache the data, you cannot uncache. It will remove once the memory gets full, it will get removed automatically. But if you persisted any data, we can unpersist it, and persistence has a different storage level as well. That's what we call it as a caching and persistence. Very good performance tuning area. Instead of, like as I was telling you, when I'm performing any of the transformations, imagine. So if I have any of the transformations, if I load the data, and if I filter any of the data, I perform another filter. And if I perform another action, if I performed an action, all right, then the data gets loaded, transformation will happen, action gets triggered, and it will be, once the action gets triggered, everything will be removed from RAM. If I re-trigger any of that, again, it will not have the data, so it will reload everything to the RAM. But in the previous action itself, if I persisted this, when this action is done, it will simply remove this data and this data. This data will stay back. If I perform any action again, some other filter or action, the data is already persisted. Like here, gym data got persisted to help you for cache data as well as credit data. That is persistence or cache. Right? Caching, persist do the same, but the cache cannot be uncached. Yes, you can perform caching also, but persistent data can be unpersisted. There's no uncache. Data.cache. If I'm persisting data.cache, it will do the same, but data.uncache, you cannot see it. All right, you cannot do that. This is cache and persistence. Persistence has different storage level as well. That's the next topic. What are the different storage level of persistence? It's a very important topic, right? Persistence. But how we can perform the different storage levels? Now have a check. If you want to persist any of the data, imagine the same code. You load the data, you do the filter, right? If you want to gym data dot persist, it will persist in memory. During another action, it just persists in memory. It's a memory only in RAM. But persistence is providing you a different storage level also. If you want to persist this intermediate data into RAM only, into memory only, yes, you can I can have it in memory only, which is a default one. It will have it in memory. But you can send this persisted data to disk also. If you have a threat of full RAM coverage or out of memory, you can send that intermediate data to disk also by introducing storage level dot disk only. I think I may need an import. Let's see. Yes, import org apache.sql._. Now you can storage to disk only. Sorry, storage. Let's see. Storage. Storage levels. Yeah, storage. This is an import statement. Import. Different storage levels. So what will happen once you load this data? You loaded the data, you filtered the data, and now you can perform different storage level. Gym data dot persist storage level dot disk only. Disk only. Now it persists only in the disk, not in memory. Yes. Now when the action is triggered, it will persist into disk, to the hard disk. If we have a threat, okay, memory might fill off in RAM. Like that, we have different storage levels. We can persist only in the memory, which is default. I can save it in memory a copy as well as a disk a copy. We can serialize the data and keep it in memory. We can serialize the data and keep in memory and disk. A copy in memory and copy in disk. We can keep it only in disk. We can keep it in 2 nodes. Memory only 2. I mean two nodes RAMs. We can keep a copy. Memory and disk. 2 copies hard disk. Off heap is just for Java. So these are the different storage levels of persistence you can perform. Alright. When I'm doing a persistence of some data, we can persist the necessary data as well. This is very important question. Please do not neglect this. Give a try if you want. Even in Eclipse, you can also give a try. Check here. In Eclipse, you want to give a try, or IntelliJ. Import org apache.sql.storage._. You can perform that underscore here. Then go to a data frame or an RDD. You can persist that. Data frame dot persist. Inside that, you can put a different storage level. Dot, if you give, you'll see disk only to disk and serialization, everything. You can persist this like this. This is what different levels of persistence in Spark. Let's go next. Array column processing in Spark. In complex data processing, we saw that we can use explode to process or filter array column, which we call it as a flattening. Let's go next. Tag in Spark. Very important question. Direct acyclic graph is a graphical representation of transformation and actions in Spark. These are finitely many vertices and edges, where each edge node directed from one vertex to another. In this case, folks, We just perform some transformation here, like 2 takes. I printed cash data and credit data. You will see when you go to the same UI, these are the 2 actions I have triggered. If you go inside a take, you can see a tag visualization, like you read it, you filtered it, you applied double filter and printed it. You'll see a tag visualization, which will help you to understand how the transformations has been taken care of. You can also see it's a graph. It will show you what each transformation action is doing. Same applies for this another action also. It's a graphical representation of the whole action performed, right? That's what I should have told you. It'll help you for debugging. It'll help you to know how many actions and transformation triggered. When we perform so many transformation and action, it'll give a kind of a graphical representation of all of your transformations and actions, right? Next, programmatically specifying schema for data frame. As I was mentioning, a schema for a data frame can be defined using struct type, which is a programmatical approach. Case class is a part of scalar, but struct type is a part of programmatically specifying a schema. Let's go next. Now let's go next. What is Catalyst Optimizer in Spark? The Catalyst Optimizer is a crucial component of Apache Spark. It optimizes structural queries expressed in SQLs or via data frames, which can reduce the runtime of program and save cost. Actually, in a very layman understanding, when we perform SQL operations, Catalyst Optimizer will design logical plan to execute the query with high performance. This can also be mentioned. So when you perform DSL operations or SQL operations like filter, group by, anything, this Catalyst Optimizer would ensure it is creating a proper logical plan to execute the query. It does automatically, but this happens at the backend when you trigger any SQL queries in Spark. Let's go next. Broadcast variable. It's very important what is a broadcast variable. Broadcast variable is a variable enables a variable data to get cached in all the necessary worker nodes, which helps for joining instead of shuffling the data, which is similar to map set join in Hive, right? So we saw map set join in Hive. So similarly, we have a broadcast as well. If we have 2 data frames, imagine I have 4 nodes, right? And I have some data sets. Imagine I have some data. Imagine this is DF1. These 2 are DF1. These 2 are DF2. Data is distributed at the back end. Imagine this way. Now what I can do, if I have DF1 and DF2, I can broadcast DF2. So what it will happen? So when I perform a join, df1.join of df2, that time, usually without broadcast, a lot of shuffling will happen to do the joins of these 2, because this belongs to df1. This belongs to df2. Now a lot of shuffling will happen to get joined. But if I perform a broadcast of df2, this data will get mapped to this whole data. This data will go and sit in all the worker nodes where I have the master data set, so that joining can happen easily, which is the same concept we saw in map set join as well in Hive. So in the code level, if you want to get into the code level, if you have 2 data frames, imagine I'm just commenting this out. Imagine if you have 2 data frames. I have read join 1 and join 2. If I want to join these two files, join 1 is a bigger file, join 2 is a smaller file. You have to always to broadcast the small table. All right. Join 2 has a small data. Join 1 has a bigger data. So always broadcast or maps or join the small table. Kindly do not forget. SC dot broadcast. I will broadcast the small table data frame. Then I perform the join. Val df join df is equal to df1 dot join of df2 sequence of transaction number. Then perform any join, inner or outer or whatever you want to perform. Join df dot show. I run this. You'll not see any difference in the output join, but this data gets migrated to the actual worker nodes. Join will happen very easily. We call it as a broadcast join. All right. In this one node, you may not see it, but get to know the syntax. This is broadcast join. All right. Broadcast variable or broadcast join. It enables the join results is going to be the same, but it enables the data sets to be available in all the worker nodes so that joining can be happen easily to decrease the shuffles. This is broadcast variable in Spark. Let's go next. Types of joins in Spark. Very important. Types of joins in Spark. We have inner join, we have left join, right join, full join, left anti-join, left semi-join, and cross join. All right. I'll be going through a document which I posted in the same doc here. Actually, one sec. Let me post it below it. Now, I posted one document. Click this document to see the details of joins. Okay. Now come down. You will see what is actually an inner join mean. What is actually an outer join mean. What is a left join. What is a right join. Left semi-join. Anti-join and cross join. Now, as a part of result, I have done the code also here. Imagine you read two data frames here. If you want to perform inner join, df1 to join of df2, column name to get join inner. So it will take only the common IDs. This is left join, left, right join, right, full join, full, right, and left anti-join. What is left anti-join? It will pick up which is not matching from the left table to the right table and show you the outputs. We already executed it. Left semi-join. Left semi-join in the sense, it will do the same left join only, but after doing the join, if we have any duplicates in the left table, it will drop. Simple. Nothing so big. Okay. Then cross join. Cross join is nothing but one-to-many mapping. All right. I'll show you that cross join. What is it? Before that, let me go through. So, inner join. You might have seen an inner join takes a common. Left join, it will take the whole left table data, but it will join with the right table. The right table means it will take the right table data common with the left. Full join, left anti, left semi, cross. Now see the result. Imagine I have two data sets. Imagine I have two data sets. All right. df1 0 1 2 3 4 and imagine I have 3. 1 sec. Okay, let me remove this duplicate 3 everywhere. Just this I have run for the testing. All right. All right. Now check the data set. Imagine you have two tables. In the first table, you have 0, 1, 2, 3, 4. Second table, you have 0, 1, 3, 7. In the inner join, it will take the common points. 0, 1, 3 are the common areas. Left join, it will take all the left table data, 0, 1, 2, 3, 4. But only when it is matching, it will put the data from the right table. But when it doesn't have data, it will put null. Same applies for right join also. It will take all the IDs from the right join, but the data switch does not exist from the left table. It will make it null. Code is available in the top. You can execute also. Full join. It will take the full data. Folks, join session I have handled separately. Please watch the detailed one. Full join means it will take the data from the first table and also from the second table. Anti-join means which are not matching in the left side. So 2 and 4 does not exist in the right table. So we are getting it anti, opposite. Left semi. It will do the same left join. But in case of any duplicates, if we face, it will drop. Cross join is one-to-many method. Like it will take the first table, map the whole second table data. Then it take the first transaction number, then it will map whole second table data. It will take the other ID for same two, it will map everything. Cross join. All right. This is joins in Spark. Please check the doc. I have sent a code as well as the document. Please verify this. Now, difference between map and flat map. Map and flat map are the functions applied in Spark RDDs or datasets. Map directly applies a function or operation. Flat map applies a function or operation along with flattening the data. What is flattening the data? Imagine I have some data set. I believe I have showed you long back, right? If I have 1, Zayo, 2, Hema, for example, if I have this data, if I do a flat map, if I do a map of split, what it will do? It will simply do a splitting. That's it. It will do a splitting from this area to this area. It will simply do a splitting. But what is flat map? It will split along with flatten the data. Each split is considered into another element. Each split is considered into an a separate element. It flattens the data. So that's the reason I have put map directly applies the function or operation to RDD or data set. Flat map applies it, but it would flatten the data. Flattening is nothing but making one element to multiple elements after performing the operation. Next, memory tuning in Spark. All right. What is memory tuning in Spark? Very important question. In case of any kind of a questions they ask, they may ask you, when you do a Spark submit, what is the syntax of Spark submit? Spark submit -- master local or yarn, right? Then you can give -- class name dot object name -- or you'll give the jar path. Actually, this is how we do the Spark submit, because we have the Spark submit -f and yarn, and then we give the class -- class name dot object name. All right. In this case, we give the jar path. We do a deployment. But in case sometimes they may ask you, if you have some node cluster, if you have 6-node cluster, how you do a memory tuning? Yes, during the Spark submit, we can do a memory tuning. When you do a Spark submit, imagine I am deploying with yarn, or local. You can do when we deal with multi-node clusters, to efficiently handle the memories of all the subnodes or worker nodes, we usually tune it by giving how many executors needs to be configured, how many num executors needs to be given, what are the executor memory I can give. These are expected parameters and driver memory. These are very expected parameter, and there is a calculation to find this. There's a very common question in interview point of view, like how will you configure this memory cores during the Spark submit? Executor cores, num executors, executor memory, and driver program. Right? How we can do it? Now let's go ahead in calculating it. Be careful when you do this calculation. Imagine I have my current cluster size is 6-node cluster, 32 vCores each, 64 GB RAM. Imagine if I have this, how many executor cores I will configure? How many num executors I'll configure? Now, let's get into this terminologies. If I have, this is my cluster capacity of 6 node cluster with 32 vcores and 64 GB RAM of each. How much I'll configure each during my Spark subnet. When you do this, check how many nodes I have, how many cores we have. Immediately write that many number of cores equals to the number of nodes. So I have totally 632s here because of 6 node cluster. Always remember, from every node, we can consider only 5 cores per job, per every executor. So always this could be 1 to 5. This could be maximum number of cores we have to allocate per node executor. So maximum always configure this as 5 because for every job it can configure only 5 cores actually. Now executor cores can be 5, but how many num executors you need to understand. Now what you have to do, since I'm going to consume 5 cores from each node, take a kind of a divide these two and find the quotient. 32 divided by 5, I approximately get 6. 5 6 are 30. Right? They'll ask you. Now in this case, if I see 32 divided by 5, I'll get 6 as a quotient. Once I got this, you have to get totally 36 num executors. This 36 num executors should be configured, but make it 35 because one executor might be allocated to application master. There is something as application master in YARN architecture. Num executors should be 35. Just ensure that you give this. What is executor memory? Yes, we can also configure executor memory. Now, take 64, take the 64 out, all right? Take the 64 out from the each node RAM, and divide it by 6. Make divided by 6. If I do 64 divided by 6, all right, I may end up with approximately 10. 10, quotient is 10, and which you get 10 minus 10 into 0.07. 0.07 is a constant variable for yarn overhead. All right. That is a very constant parameter to do this. So approximately I'll get 10 minus 1. When 10 minus 0.7, I'll get 9 GB. So executor memory should be 9 GB. This is how we have to calculate it. I'll do one more example, so don't worry about it. Now check. My executor cores would be 5. Num executor I got 35. Executor memory I got approximately 9G as a parameter to be passed. Driver memory could be anything because it depends on the memory. Driver in the sense only the master node. In that you can provide as per the memory you have. If you have 256 GB RAM, make it 256 GB, doesn't matter. Or approximately 255 or 250. Depends. Driver memory will not have a significant calculation. You can give as many. You can give 10 GB, 20 GB, or 40 GB, just to collect the metadata, right? That doesn't matter. But this is your configuration for this node cluster. All right. Let's find another. Let's find the same for the different node category. All right. Imagine if you have 4 node cluster, 64 cores, 32 GB RAM. If you have 4 node cluster with 64 cores and 4 GB RAM, how much you will find with the same calculation? What would be your weak executor cores, num executors, and executor memory? In this case, as I was telling you, take 4 nodes, right? Write 64 4 times. Once you write 64 4 times, you have to take only 5 cores each. That is no change in that. You have to definitely take 5 cores. No change. Now put that 5 each. 64 divided by 5. Then you have to take V cores. 64 divided by 5. You may get approximately quotient is 12. 12, 12. Now do an addition of all this 12, you will get 48. 48 as a total. So mention the num executors as 47 because we have to allocate one core for one executor for application master. Once this is done, to find executor memory, take this 32, take this 12. All right, take this 12, do a division out of it. You may get around, check here folks, you may get around 12 twos are, right? Just imagine if you're making the 32 divided by 12. When you do this quotient, approximately I may get around 1 GB because almost I'm consuming a lot of information for memory tuning, right? So if I make 32 divided by 12, I may get around approximately 3 because 12 3s are 36 kind of. 3 minus 3 into 0.07. Approximately you get 2 G. So the executor memory you have to allocate is 2 GB for executor. This is a configuration for this type of nodes. This is a configuration for this type of nodes, right? Let me calculate the last time. All right, check here. I have, for example, 5 node cluster, 16 V cores and 64 GB RAM. In this case, how to do the calculation? The last calculation, what you have to do first, since I have 5 nodes, write the cores that many times, 16 and 16. So I have to do the calculation of this right now. Take it and write it down here. Now cores are always common, so executor cores can be 5, right? Then put 5 against each. Put 5 against each. 16 divided by 5. So how much you will get? The quotient would be 3, 3, 3, 3, and 3. Now take the total of all these 3. You'll get around 15 executors in total. The num executors would be 14. All right, because one for application master. Now to find the executor memory, 64, take this, 64 divided by 3. What is a quotient? You'll get around 21 minus 21 into 0.07. 0.07 is yarn overhead. If you make this, you may get approximately 2. This becomes 2. 21 minus 2, 19. You have to do 19G as a calculation. So this is a calculation you have to give for this type of cluster. When you do the Spark Summit, this is a pretty common question asked. How will you calculate the number of, for example, how you calculate the cores and executor for this. Kindly consider it's very, very important. All right. Yeah. So take this calculation. Definitely it is important. I'm making this calculation into a separate notepad. I'm giving that to you. That's it.